So I was trying to book a quick getaway to San Francisco last Tuesday. It was late, I was tired, and I did what everyone does now. I opened up a chatbot, one of the big ones,
Right.
and I just typed, "Plan me a weekend trip from San Diego." And honestly, at first it was impressive. It spits out this beautiful, perfectly formatted list, morning flight suggestions, a boutique hotel near the wharf, even a dinner reservation at a place I actually like.
It felt like magic. The answer just appeared.
It felt like magic for about 30 seconds, and then it hit me. I still had to do everything.
Ah, the reality check.
Exactly. The bot gave me a list of text. It didn't book the flight. It didn't reserve the table. It didn't charge my card. It was just a glorified search engine result that could talk back to me.
Right, and that little moment of frustration you felt, that is the exact boundary line in artificial intelligence right now. It's the friction point between the systems we have, which are, I mean, they're brilliant at generating text,
Yeah.
and the systems we actually want.
Which are systems that can do things.
Systems that can execute tasks. It's the fundamental difference between a talker and a doer.
And that is precisely where we're going today. We aren't talking about the next version of ChatGPT that writes slightly better poetry. We are talking about something else entirely. Agentic AI,
Mm-hmm.
systems that have agency, autonomy, and this is the crazy part, the ability to negotiate with other software to actually get stuff done in the real world.
And to guide us through this, we're doing a deep dive into a really timely source. It's a new book just out in 2025 called Building Agentic AI Systems. The authors are Anjanava Biswas and Rick Talikdar.
I was looking into them, and that's what got me excited. These aren't just academics. They come from the trenches, right? We're talking Amazon, IBM, Oracle.
Exactly. And the forewords for the book, they're from heavy hitters at Microsoft Research and Minset.ai. I mean, these are the people actually building the plumbing for the next generation of the internet.
So this isn't a sci-fi novel. It's more like a technical blueprint. And the mission for this deep dive is to unpack exactly how we bridge that gap from, generative to agentic.
Yeah.
We really need to understand how a piece of software evolves from a tool you just talked to into a system that has the authority to go out and negotiate on your behalf while you sleep.
Right. But to understand where we're going, these do-bots, if you want to call them that, we have to make sure we're really solid on the engine that's powering them. We have to start with the foundation.
Generative AI.
Generative AI. Because you can't have an intelligent agent without, well, the intelligence part.
The book kicks off with this distinction that I think most people sort of get intuitively but maybe haven't put words to. And that's the difference between generative and discriminative AI. They use this artist versus critic analogy.
It's the best way to visualize it, I think. For the last decade or so, most of the AI we actually dealt with was discriminative.
Okay.
So think of it like a snobby art critic. You showed a picture and it just says cat or dog or, hot dog.
It's just classifying things.
It is discriminating between classes of data. It's mapping an input to a label. It doesn't create anything new. It just categorizes what's already there.
But generative AI, that's the artist.
Yes. The generative model doesn't just label the cat. It studies millions of pictures of cats until it learns the mathematical essence of catness. It understands the probability distribution of a whisker versus a tail, a fur texture, of ear shape.
And then it can create a new one.
And then it can create a totally new image of a cat that has never, ever existed in reality. It samples from that learned probability distribution to generate a brand new instance.
To get to that point, though, the authors take us through a bit of a history lesson, which I found really useful because it frames the limitations that we're still dealing with now. They start with VAE's variational autoencoders.
VAEs were a huge stepping stone. The book uses this art student analogy for them, which I think is pretty good.
I liked this one. So, you have an art student, and they're trying to learn how to paint a masterpiece. The VAE works by taking a complex input, like a really detailed painting, and forcing the student to compress it, to turn it into a tiny, quick sketch.
And in technical terms, that little sketch is the encoding. It's being encoded into what's called a latent space.
Okay, latent space. What does that mean in simple terms?
It's just a highly compressed mathematical representation of the data. Think of it like this. Instead of storing every single pixel of the painting, you're storing a few key numbers that describe its core features, like color palette, subject's pose, style. That's the latent space.
Got it. So you've got the sketch. Then what?
Then the student has to try to recreate the full high-resolution painting using only that sketch. That's the decoding part of the autoencoder.
And the whole point is, if you can actually recreate the masterpiece from just that tiny sketch, You must have learned something fundamental about the structure of the image.
Exactly. You've learned the essential features, and just as importantly, you've learned to discard the noise. You know what matters.
And this isn't just for making art. The book brings up this fascinating real-world example with AstraZeneca.
Yeah, this is where it gets really powerful. They used VAEs not for art, but for drug discovery.
So instead of compressing paintings into sketches, they were compressing, what, molecular structures?
Precisely. They treated chemical structures as a form of data. By encoding them into that latent space, they could suddenly do math on molecules. They could explore the space between existing drugs.
What do you mean walk through the space?
I mean, they could take the mathematical point for one drug and the point for another drug and find a halfway point in that latent space. Then they could decode that new point back into a chemical structure.
And it would be a brand new molecule.
A brand new molecule that scientists hadn't invented yet, but which had properties that were a hybrid of the two originals. They were effectively sketching new medicines into existence.
That's incredible. But VAEs, they had a problem, right? The book mentions the output was often a bit blurry.
It was. The sketches were good, but they weren't photorealistic. The reconstructions were a little fuzzy, a little averaged out,
Yeah.
which is why the field really took off when it moved to Jan's generative adversarial networks.
This is the counterfeiter versus detective game.
Yes. And I feel like Jan's were the moment the general public really started paying attention, especially with things like deepfakes.
For sure. So how does this game work?
In a Jan, you have two neural networks that are locked in a fight to the death. One is the generator. That's the counterfeiter. It tries to make fake data, like a fake dollar bill or a fake photo of a celebrity.
And the other one is the discriminator, the detective.
Right. The detective's only job is to look at an image and say real or fake.
And they learn by competing with each other.
It's a zero-sum game. It's adversarial. Every single time the detective spots a fake, the counterfeiter gets a little signal back that says, that didn't work, try something else. It learns, it gets better.
And every time the counterfeiter manages to fool the detective.
The detective gets a penalty and has to get sharper. They bootstrap each other's performance. Eventually, the counterfeiter gets so good that its fakes are statistically indistinguishable from the real data. The detective is basically just guessing, 50-50.
At that point, the generator has learned the true data distribution. It's a perfect artist. The book mentions a specific type, StyleGAN. That's the one that lets you separate the style of an image from the content, isn't it?
Exactly. It disentangles the features in that latent space we talked about. So you can take the content of, say, a photo of a cityscape and the style of a Van Gogh painting and mix them together. You get the cityscape painted in the style of Van Gogh. It was a huge breakthrough for creative applications.
But even with all that power, GANs weren't the thing that gave us the chatbots we have today. The book makes it clear that the real revolution, the engine that powers the agents we're really here to talk about, is the transformer.
The transformer. This is the architecture behind the T in GPT, and it changed everything.
The book describes the key innovation here as the self-attention mechanism. And I think this is where we need to slow down and really unpack it.
This is the critical piece. Before transformers, if an AI wanted to process a sentence, it did it sequentially, word by word by word. It was like reading a long novel through a tiny little peephole.
You only see one word at a time.
You only see one word at a time. It was slow, and it was terrible at remembering context. By the time it got to the end of a long paragraph, it had completely forgotten what the beginning was about. They had these clunky things called LSTMs to try and carry memory forward, but it was really inefficient.
So how does the transformer fix that? The book uses a cocktail party analogy, but I want to go a bit deeper. How does self-attention actually work on a technical level, but, for the rest of us?
Okay, so forget the people. Imagine you can see the entire paragraph all at once. The transformer does that. It takes in the whole chunk of text, and for every single word, it asks a question. How important is every other word in this text to understanding this specific word?
So it's not reading left to right. It's building a web of relationships.
Precisely. It assigns a numerical weight, or an attention score, to how much every word should pay attention to every other word.
Give me an example.
Okay, so if I say the animal didn't cross the street because it was too tired, the model needs to know what it refers to.
Right. The animal or the street.
A human knows instantly. A transformer learns this by assigning a very high attention score between the word it and the word animal, and a very low score between it and street, because it's learned from billions of examples that animals get tired, streets don't. It holds that context across massive amounts of text.
And that ability to hold context, to understand the relationship between the beginning of a request and the end of a request, is what allows for complex reasoning.
It's everything.
Which brings us to the core argument of the book.
Mm.
We have these incredible engines. They can write code, they can summarize novels, they can pass the bar exam, but they can't do anything.
That is the aha moment of the whole book. A generative model is, at its heart, a probability engine. It's just a machine for predicting the next most likely word.
But an agent is a workflow engine.
It's a workflow engine. It executes a task. And the book pivots right here to explain how we bridge that gap. They walk us through this case study that I think is really, really illuminating, the flight booking assistant.
Okay, let's dig into this case study. Because on the surface, it looks exactly like what I did with that chatbot last Tuesday. You type, "Hi, I want to fly to San Francisco." The bot replies. Simple. But the book breaks down what it calls the backstage process, specifically in Figure 1.2, and it is radically different from a standard LLM conversation.
It is. In a standard chat, like the one you use, the AI is just, it's hallucinating a plausible-sounding response based on its training data. When it says, "I've found these flights," that's just text it's generating. It didn't find anything.
It's like pretending.
It's pretending. But in an agentic system, the model engages in a process that the researchers call chain of thought reasoning, or COT.
Okay, so walk me through that chain. I type, "Fly me from San Diego to SF next Friday." What does the agent do first?
It doesn't answer you immediately. This is the key. It stops, and it essentially talks to itself. This is the planning phase.
Yeah.
The agent looks at your prompt, and it thinks, okay, the user's ultimate goal is book flight. To call that function, what information do I need? I need an origin, a destination, a date, and the number of passengers.
So it's like checking the arguments for a function in programming.
That is exactly what it's doing. It continues its internal monologue. Do I have the origin? Yes, San Diego. Do I have the destination? Yes, San Francisco. Do I have the date? Yes, next Friday. Do I have the number of passengers? No, that's a missing parameter.
So it realizes there's a gap. It knows what it doesn't know.
And that is a huge leap in intelligence. So, because it has a gap, it generates a plan. My next step is to ask the user for the number of passengers. It then pauses its execution, sends that specific question out to you, and waits for your response.
Okay, so I replied just one passenger. Now it has all the variables it needs. In a normal chatbot, this is where it would just make up a flight and a price. But the agent uses a tool.
This is the critical differentiator,
Yep.
tool use. The agent has been given access to a library of external functions, or APIs. It sees that it has all the info for the flight lookup tool. So it constructs a piece of code on the fly.
Literally writes code.
Yes, it forms a function call like flight lookup, origin SAN, destination SFO,
Yeah.
date 2026-0205, passengers 1, and then it executes that code.
So it's actually hitting a live API like a United Airlines or Kayak API and getting a real-time JSON response back with real flight data, real prices, real availability.
Precisely. No more pretend. It gets that raw data back, and then it goes into the reasoning phase again. It doesn't just dump that messy JSON data on you. It parses it. It looks at the results.
Right.
Maybe it sees a United flight for $400 that lands at 9 a.m. and an Alaska flight for $350 that lands at 10 a.m. It compares them. It might check a secondary weather tool to see if there are likely delays. It might check your known preferences and see you prefer Alaska. It reasons about the options.
And then it presents me with a recommendation. And the final step, if I say, book the Alaska one, is execution.
It triggers a completely different tool,
Oh.
the Book Flight API. It passes your payment information, confirms the seat, and actually spends your money. Then it might call a send email tool to send you the receipt.
That loop plan, tool use, reasoning, execution, that's the whole game.
That is the definition of agentic AI. It moves the system from being a passive library of information to an active participant in the digital world. It's not just predicting words, it's manipulating APIs and getting things done.
This brings us to the anatomy of these agents. Chapter 2 in the book is, it's pretty dense on definitions, but they are really important. The authors break it down into 3 conceptual pillars: self-governance, agency, and autonomy.
And we need to be really careful here, because in casual conversation we use these words, especially agency and autonomy, almost interchangeably. But in computer science and AI, they have very, very specific meanings.
Okay, let's start with the first one, self-governance. To me, that just sounds like it runs itself.
That's basically it, yeah. Self-governance means the system controls its own internal state and processes. It doesn't have a human puppeteer clicking next for every little internal calculation. It's about resilience and self-management.
So an example would be, What?
If the flight lookup API times out and returns an error, a self-governing system doesn't just crash. It detects the error, it logs it, and its internal logic might say, retry up to 3 times. If it still fails, switch to the backup Expedia API. It manages its own health without human intervention.
Okay, that makes sense. It's robust. Then the next one is agency.
Agency is all about representation. It means the system has been given the authority to act on behalf of someone or something
On my behalf.
on your behalf. And this implies 2 critical things. First is intentionality. The software has a goal, get the user to San Francisco, and every action it takes is intentionally driven by that goal. Second is responsibility. In some sense, the agent is answerable for the outcome. If it books the wrong flight, it failed in its agency.
And finally, autonomy. This is the one I really want to spend some time on because the book makes this distinction between operational autonomy and functional autonomy. And I felt like this distinction is where all the power and, frankly, all the potential danger lies.
It is the most critical distinction in the entire book. It's where this technology goes from being a useful tool to something else.
Okay, so break it down. Operational autonomy.
Operational autonomy is straightforward. It's the ability to execute a defined task from start to finish without human help. Think of a robotic arm on a car assembly line. Its task is to weld a door frame. It does it perfectly, thousands of times a day, with no one holding the torch. It is operationally autonomous.
But it's just following a script. It's doing the exact same thing every single time.
Right. And here's the key. If a car comes down the line with a giant dent in the door, the operationally autonomous robot will just weld right over the dent. It has no concept of the higher level goal. Its only instruction is weld.
And functional autonomy is different how?
Functional autonomy is the ability to make choices and change its own behavior in order to better achieve the goal. It's about adapting the plan. A functionally autonomous robot would see the dent and realize that welding it would violate the higher level goal of build a quality car.
So it would stop.
It would decide to stop the line or reject the part or flag a human for help. It makes a decision that wasn't in the original script because it understands the intent behind the task.
So let's apply that to our software agent. Operational autonomy is successfully executing the book flight API call once I tell it to.
Yeah.
Functional autonomy would be, what? It realizing the flight is way too expensive and deciding to look at trains instead, even if I never explicitly asked it to look for trains?
Exactly that. Or it might see that your goal is get to SF by 9 a.m. for my meeting. It checks all the flights and sees that due to fog, nothing is going to land before 10 a.m. A functionally autonomous agent might decide, on its own, to book you on a flight the night before and add a hotel room to the itinerary because it determined that was the only possible way to achieve your stated functional goal.
Wow, that is an incredible amount of power, and it's an incredible amount of trust you have to place in the system.
It is. You are giving the system permission to change the plan, not just execute it.
The authors actually give us a peek under the hood at the code logic that drives this. They outline a trip planner algorithm. It's algorithm 1 in the book. I was looking through the steps, and it's surprisingly simple and logical. It's not magic. It's a loop.
It's a very standard control loop, yeah. You see similar things in robotics and automation. Step 1 is set goal. The agent passes your natural language request, book me a trip, and translates it into a structured, machine-readable objective.
Then step 2 is update knowledge. This is where it's hitting those APIs we talked about.
Right. It calls the tools, gets the flight and hotel data back, and stores the results in its short-term memory, which they call the knowledge base.
And then step 3 is scoring. This is the part I found really interesting. The agent scores the options autonomously. It decides what's good.
Yes. This is where a lot of the reasoning happens. It assigns a numerical score to each potential itinerary based on criteria that it knows are important. Those criteria could be programmed in, or they could be learned from your past behavior. It knows you value price over duration, or that you prefer nonstop flights. So it scores each option.
And the final step is make decision. It just picks the winner based on the score.
It picks the highest scoring option.
But the key here, and this gets back to autonomy, is that the make decision function runs inside the black box. It doesn't pop up a little window and ask me, hey, is this scoring okay with you? It just decides.
That's the autonomy. Once you set the goal and press go, the loop runs until it finds a solution or fails. It's an active participant, not a passive tool.
So we know what the agent is doing, this loop of planning and acting. But how is it organizing its thoughts? How is it structured? The book moves into section 4 here. architectures of intelligence. And it turns out there isn't just one way to build an AI brain.
No, and this is a debate that goes all the way back to the earliest days of AI in the 1950s. The book outlines three main architectural patterns. The first is the deliberative architecture. You can think of this as the thinker.
Slow, methodical, calculating.
Very. It's classic old-school AI. It operates on a cycle called sense, plan, act. First, it senses the entire state of the world. It tries to build a complete, perfect, symbolic model of its environment.
Like a map of everything.
A map of everything. Then, using that map, it formulates a complete optimal plan from start to finish. It thinks through every possible consequence. Only after all that thinking does it take the very first step of the plan.
It sounds like a chess computer, like Deep Blue. It calculates 20 moves ahead before it even touches a pawn.
That's the perfect analogy. It's symbolic, knowledge-based AI. The pro is that it's fantastic for complex, static, perfectly defined puzzles like chess or logistics planning. The con is that it is incredibly slow. It's computationally expensive. And in a dynamic, messy, real-world environment, it fails completely.
Because by the time it finishes making its perfect plan, the world has already changed.
Exactly. If you're building a self-driving car and a child runs into the street, you cannot use a deliberative architecture.
Yeah.
You can't afford to say, sensing child,
Mm-hmm.
updating world model, calculating child's velocity, checking physics engine, planning optimal braking trajectory.
You'll hit the child.
You'll hit the child. You
Yeah.
need to react instantly, which leads directly to the second architecture, reactive, the reflex.
Okay, so this is the opposite.
The complete opposite. The reactive architecture is pure stimulus response. There is no internal model of the world. There is no memory. There is no planning. It's just a collection of hard-coded condition action rules.
If X happens, do Y.
That's it. If obstacle detected less than 2 feet ahead, turn left. If ambient temperature exceeds 100 degrees, activate cooling fan. If fire detected, run.
So it's blazing fast.
Instantaneous. And it's incredibly robust because it's so simple. It doesn't get confused by complex plans, but it has absolutely no foresight. It can't plan to do anything. A purely reactive robot can vacuum your floor by just randomly bouncing off walls, but it can't plan a vacation. It doesn't even know what a vacation is.
So you have the slow, smart thinker and the fast, dumb reflex. Naturally, the answer is to combine them. The hybrid architecture.
The hybrid approach is what almost all modern agentic systems and robots actually use. It's a layered structure. You get the best of both worlds. You have a reactive layer at the bottom, connected directly to the sensors and actuators, handling the immediate fast stuff.
The reflexes.
Reflexes. And you have a deliberative layer sitting on top, handling the long-term goals and the complex planning.
The book uses the driver analogy again here, which I think really nailed it.
It's the perfect way to think about it. When you're driving to a new city, your deliberative brain is navigating. You're thinking about the overall goal. You're looking for street signs. You're checking the GPS. You're planning which lane you need to be in for the exit that's 3 miles away. That's the high-level plan.
But at the exact same time, my hands on the wheel and my foot on the brake are doing something else entirely.
Your reactive brain is handling that. It's keeping the car centered in the lane. If a pothole suddenly appears right in front of you, you swerve. You don't think about it. You just do it. It's a reflex. An effective agent needs both. It needs to deliberatively plan the complex flight itinerary, but if the flight API suddenly returns a 500 server error, it needs to reactively and instantly retry or switch to a backup server without crashing the whole system.
That makes perfect sense. So we have a smart hybrid agent, but the book argues that even a single agent, no matter how smart, is limited. The real power and the real future comes from multi-agent systems, or MAS.
This is where it starts to get really sci-fi. Because the reality is, a task like plan my vacation is too big and complex for one single bot. It involves flights, hotels, rental cars, restaurant reservations, weather checks, budget constraints. Trying to stuff all of that specialized logic into one monolithic model is messy and inefficient.
So you build a team, an ecosystem of specialized agents that talk to each other.
Exactly. You have a travel agency agent that acts as your personal representative. But then it doesn't try to know everything about airlines. Instead, it goes out and talks to a separate, specialized airline agent that represents United. And it talks to a hotel agent representing Marriott.
And the book uses a key word to describe this ecosystem: heterogeneity.
Yes. And that's crucial. It means they're all different.
But it doesn't just mean they're built differently. It means they have different and often conflicting goals.
Now you're getting to the heart of it. This is where it gets really complicated and really interesting. If your agent's primary goal is to get the cheapest possible price, And the airline agent's primary goal is to get the highest possible price. They are, in effect, adversaries.
So how does anything ever get done? Are they just fighting?
They negotiate. And this isn't just a metaphor for a complex search. The book describes formal interaction mechanisms where agents mathematically haggle with each other.
I want to try and visualize this. Let's say I'm the user agent. My goal is book a flight to London for under $600. You're the airline agent. Your goal is maximize revenue for this flight. What happens?
Okay, so your agent sends me a request. My airline agent checks its internal database. I see the flight to London is currently half full. I also see that it's a popular route, so demand is likely to increase. My goal is to maximize revenue, so I make the first offer. I propose a price, $800.
My agent receives that offer. It checks its internal rules, its utility function. The utility, or the value, of paying $800 is negative because it massively violates my budget constraint of $600. So my agent instantly rejects the offer. But instead of just giving up, it formulates a counteroffer.
Yeah.
My agent says, I cannot pay $800. I will pay $550, but I will accept a non-refundable ticket with no free checked bag.
No, that's interesting. Now, my airline agent has to evaluate that counteroffer.
Yeah.
The $550 price is lower than I wanted,
Yeah.
but non-refundable is a valuable term for me. It increases my utility because it guarantees the revenue and reduces my risk. No checked bag also saves me money. My internal math says that the combined utility of this deal is positive, so I accept.
And this entire negotiation, this back and forth of offers and counteroffers based on mathematical utility, happens in milliseconds via API calls.
Yes, a flurry of messages between agents, each one trying to maximize the utility for their respective human, completely autonomously.
That implies a fundamental shift in what the internet even is. It changes the web from a place where I go to look at prices on a web page to a place where my software goes to fight with your software in a digital marketplace.
It becomes a marketplace of bots.
Yeah.
It's no longer about human-to-computer interaction. It's about computer-to-computer interaction on our behalf. And this leads to massive efficiency, but also, as you can imagine, massive complexity.
How so?
Because now you have to define those utility functions very, very carefully. If you're lazy and you just tell your agent, get me the absolute cheapest flight no matter what, you might get an unexpected result.
Like what?
It might negotiate a fantastic ticket price for you, with a 48-hour layover in a war-torn country. Because mathematically, that was the optimal solution that satisfied your simple, poorly defined utility function for price.
Which brings us perfectly to the reality check. This is section 6 in the book, and I'm really glad the authors included this because it would be so easy to just hype this technology up forever. But there are real, serious technical walls we're hitting, and the first one they mention is the oldest one in the book: bias.
Garbage in, garbage out. That's the first rule of computing, but with agents, the stakes are so much higher. If a generative model is biased, it says something offensive or incorrect. If an agent is biased, it does something discriminatory. It denies someone a loan. It rejects a job application.
The book uses the specific technical example of imbalanced data. Can you explain that with the Class 0, Class 1 example they gave? It was really stark.
Sure. Imagine you're training an agent to pre-filter job applicants for a software engineering role. You feed it a historical data set of all the successful hires your company has ever made. Let's say in your data, Class 0 is men and Class 1 is women. Now, if your company's historical hiring data is, say, 90% men Class 0, the model learns a very simple but very wrong lesson. It learns that being Class 0 is a very strong predictive feature of being hired.
So it effectively learns to just ignore Class 1.
It treats the minority class as noise, as an anomaly. It overfits to the majority. So when you deploy this agent to run autonomously, it might just automatically filter out highly qualified female candidates, not out of malice, but because the cold hard math tells it that's the statistically safe bet to predict a successful hire.
And how do you fix that?
Well, the book discusses some technical fixes like oversampling, which is literally just duplicating the data from the minority class thousands of times to force the model to pay attention to it, or undersampling, where you throw away data from the majority class. But these are really just band-aids on a much deeper societal problem reflected in the data itself.
Then there's privacy. I have to say, I was genuinely shocked by the $200 attack that's mentioned in the source. I knew LLMs were kind of leaky, but to do it that cheaply.
It's terrifyingly cheap, and it's a huge problem. This was a real study. Researchers targeted a production model GPT 3.5 Turbo. They didn't hack the servers. They didn't breach any firewalls. They just used the public-facing API, just like any other customer.
And they spent just $200 on queries.
About $200.
Yeah.
And by using clever prompt injection techniques, basically asking the model questions that trick it into revealing its training data, they were able to extract reams of private information.
What kind of information?
Names, email addresses, phone numbers, snippets of legal documents, real PII, personally identifiable information that the model had memorized verbatim during its training process.
So if I build a medical diagnosis agent for a hospital and I train it on a bunch of sensitive patient records.
That data is potentially discoverable by anyone with $200 and a clever prompt. It's a fundamental vulnerability. The author suggests some mitigations, like using small language models or SLMs as a kind of privacy filter.
How would that work?
The idea is you have a small, secure, maybe even a dumb model that runs locally. Its only job is to scrub the data of all PII before it gets sent to the big, smart, leaky brain in the cloud. But that adds latency, it adds complexity, and it adds cost.
And speaking of cost compute, running these agentic loops isn't free.
It's far from free. A standard Google search costs a fraction of a cent in electricity and processing power. An agentic loop. Think about that cycle we discussed. Plan, tool use, reason, execute. That might involve 10, 20, 50 separate calls to a massive large language model.
Each one costing money.
Each one costing money and consuming a significant amount of energy. The financial cost and the environmental cost are orders of magnitude higher than simple search.
So we might actually see a world where only wealthy individuals or large corporations can afford to have powerful do bots, and the rest of us are still stuck using search bars.
That is a very real economic risk. The digital divide could become an autonomy divide.
And finally, the classic AI problem, hallucinations. But again, with agents, the stakes are just completely different.
They're so much higher. If ChatGPT hallucinates a historical fact in an essay you asked it to write, you get a bad grade. It's embarrassing. But if banking agent hallucinates a decimal point in a transaction,
Or if our flight booking agent hallucinates a flight that doesn't actually exist,
and then it tries to book it with a book flight tool, which then fails, causing a cascade of other errors. The core problem, as the book notes, is confidence. LLMs rarely say, "I don't know." They state their hallucinations with the same confident, authoritative tone as they state facts. Agents amplify this risk because they are designed to act on that misplaced confidence.
So, okay, we've covered the tech. We've gone from the early days of VAEs and CANs up to the transformer. We've looked inside the agent's brain, that loop of plan, tool, act. We've even seen how they might negotiate with each other. It's a massive, massive evolution. But I want to circle back to the listener. Why does this matter to them right now?
Because the internet, as we've known it for 30 years, is fundamentally changing. For most of its life, the internet was a library. You went there to read things, to consume information. Then it became a media channel. Now it is actively becoming a workforce.
A workforce. I like that.
If you are a business owner, you can no longer just build a pretty website for human eyeballs. That's not enough. You need to build robust APIs for agents to talk to. If your pricing data or your inventory isn't machine readable, you will be invisible to the bots that are increasingly making the actual buying decisions.
And if you're an individual, a knowledge worker,
Your productivity and maybe even your value in the marketplace is going to be defined by how well you can manage and direct your own personal fleet of agents. It's not going to be about how fast you can Google something anymore. It's going to be about how effectively you can delegate tasks to your digital workforce. It's a shift from searching to managing.
which brings me to the final provocative thought I want to leave everyone with. And it's something the authors brought up that has been stuck in my head. They talked about functional autonomy.
Yeah.
That ability for the system to change its own strategy to hit a goal.
Right, adapting on the fly without asking for permission.
If we have these agents out there negotiating prices, choosing our hotels, and changing their strategies without us watching, at what point does the assistant become the manager?
That is the ultimate question, isn't it?
I mean, think about the downstream effects. If my agent's utility function leads it to decide that United Airlines is consistently inefficient or too expensive, and it just stops booking flights with them, and a million other people's agents running on similar logic all do the same thing, that airline could go out of business.
The agent is no longer just suggesting flights. It's actively shaping the market in a way no human is directly controlling.
It's the principal agent problem, but on a global algorithmic scale. Are we actually ready to trust an algorithm that doesn't just suggest a purchase, but autonomously spends our money based on its own internal and probably inscrutable mathematical logic?
And are we ready for the day when the agent looks at the goal we gave it and at the way we're trying to help and decides that we are the inefficient part of the process that needs to be managed around?
Let's hope they put a very sturdy safety rail on that function.
Let's hope so.
Something to chew on next time you ask a chatbot to just handle it. Thank you for listening to this deep dive into building agentic AI systems. We'll see you next time.